Kia ora and welcome to video 16 in the series Insightful Integration. In this problem, we have a surface area question. So it's another application of integration. We've seen integrals for areas, we've seen integrals for volume in the series, and surface area is just something else you can do with integration. If you're interested in the derivation of this formula, then I encourage you to look it up. There's different sources like Wolfram Alpha and various other websites that will show you. But if you're not so worried about that, you're just chucking these equations, the parametric equations x and y, into this formula. But before we do that, we have to differentiate them. We're squaring, we're adding, we're square rooting. It looks very much like Pythagoras. And you've got to be very, very careful with your derivatives and with your algebra, because those terms there are both under a square root, which means if it's going to simplify, there's going to be a nice substitution, or the thing underneath the square root is going to simplify such that you can take its square root. I was trying to give you a cryptic hint there, but I think I just confused. So be careful and be prepared. Maybe go grab a cup of coffee here. Be prepared for a solution that does blow up a little bit, but it does eventually simplify quite nicely. All the best, and we'll catch you for the solution shortly. Okay, so this problem is pretty brutal. We're given this formula that gives us a surface area of a solid, and a few videos ago we did a problem that looked at the volume of revolution. This one here is the surface area of revolution, and we've got a parametric curve this time, so we've got this unfamiliar formula that we need to use. The first thing that we need to do in the formula is find these derivatives, and be very, very careful in finding them, because one slight error is going to mean that this integral doesn't simplify. It's an integral of a product of two things. We better hope it simplifies, otherwise we're going to be left with something like integration by parts, or just a giant mess that we need a computer to solve. Okay, but given that the equations have similarities to them, they've both got the same denominator for a star, and there's the conjugate kind of thing on the top of the y expression, it's probably going to simplify for us if we're careful. So first up, if we find those derivatives, so dx dt, well, let's just use chain rule for that one. Bring the denominator up to the power of -1, dx dt, take the -1 to the front, drop it to -2, and then multiply by the inner derivative, and then tidy it up. Okay, and that doesn't simplify, unfortunately. And do the same thing for the dy dt. This time we'll use the quotient rule though. So we've got y e to the t minus e to the minus t all over e to the t plus e to the minus t. Okay, so diff the top expression multiplied by the bottom expression, minus differentiate the bottom expression multiplied by the top expression, all divided by the bottom expression squared. And there is some cancellation when we expand things, and I'll leave that for you to check, but when we simplify this, it comes out to be 4 over e to the t plus e to the minus t all squared. So expanding out those brackets, things do cancel. Okay, the next step is to chuck both those things into this formula, the integral formula that we're trying to find. The surface area is 2 pi, integral between 0 and 1, those are the lower and upper bounds of t, the parameter that we're using. It doesn't necessarily mean time, but it's, it could be theta or whatever. They've just chosen t to be the parameter. And then we've got y. Well, yeah, y is that whole beast of an expression. E to the t minus e to the minus t all over t plus e to the minus t times by the square root of dx dt all squared and dy dt all squared. Okay, so the first one, 4 e to the t minus e to the minus t all squared over e to the t plus e to the minus t all to the 4, that's dx dt all squared, plus 16 over e to the t plus e to the minus t to the power of 4. So the first thing we can do is pull the e to the t plus e to the minus t, the denominator stuff. We can pull it, because on both of them we can pull it out of the square root. When we do that, it's going to be a squared, and there's already one out there. Right, there's one sitting there as well, so it's going to become a cubed if we do that. Okay, and then we're integrating the square root of something that doesn't look very nice. Like a simple substitution is probably not going to help in this situation. We're going to need to do something algebraic. There's going to be like a magic trick that happens. So let's try and find that magic trick by simplification. So usually something like this will turn into a perfect square, and then you can square root it. So if we expand this stuff, we've got 4 e to the 2t, so that's e to the t all squared, and then we've got 4 e to the minus 2t, and the middle terms, okay, when we take these dudes here and multiply them together, we get e to the 0, which is 1, and we get two lots of that with a minus, so it's minus 2 times the 4 out the outside, we've got minus 8, and then plus 16. And that's really useful because the minus 8 and the plus 16 go together to make plus 8, which is very similar to what we had underneath the square root when we expanded that first bracket. The only difference was it was a minus 8. So we can factor this as e to the t plus e to the minus t all squared, with a plus there rather than a minus. And if you're not convinced of that, check by expanding. You'll see that it comes out to be exactly that. So all we've done is take the 16 and merge it inside the brackets as a perfect square. Okay, so let's get rid of all that now. We've tidied it up. Move that underneath there, and because it's a perfect square, we can square root it. And when we square root that, so we've got 2 pi, 0 and 1, we're going to get a 2. Instead of a square root of 4 is 2, we're going to lose the squared on the e to the t plus e to the minus t, and that's going to cancel off one of the denominator. So we're going to end up with 2 e to the t minus e to the minus t all over e to the t plus e to the minus t squared. Okay, now I'm going to use a substitution. And if in doubt, make something in the denominator the substitution. So if I tried a couple of substitutions, to be honest, but this is the one that worked for me. If I go e to the t plus e to the minus t as my substitution, remember whenever you make a substitution you should differentiate it as well. So du is e to the t minus e to the minus t times dt. Okay, usually you write du dt, but then I just brought the dt up there, write it using differential notation. And then that's great because that whole thing there is equal to du. And the thing on the bottom is 2 over u squared. Also, because of the limits were t values, right? That was t1 and that was t2. We should change those. So when we go t is equal to 0, the bottom limit, u is equal to e to the 0 plus e to the 0, so 2. And when t is equal to 1, e to the 1 plus 1 over e. So e plus 1 over e. It's not that nice, but the rest of the stuff becomes very simple. The integral simplifies a lot. So we started off with something really horrible, but we're now integrating something fairly simple between 0, so that was u is equal to 2, e plus 1 over e. Don't forget the 2 that's sitting up there, 2 over u squared du. Okay, that's not, you would hate to get right through to here and then think that's a log. Remember 2u to the minus 2 anti-diffs to 2u to the minus 1 over minus 1. So we've got minus 2 over u between e plus 1 over e and 2, all multiplied by 2 pi. Okay, so if we evaluate that, I'm just going to do it on the graphics calculator. It comes out to be 2.2113 to 4 decimal places. There is an exact form, but it isn't really very nice.